When organizations collaborate on a shared blockchain network, they operate under the assumption that their internal data and transaction histories are private. For decades, enterprise privacy relied on a walled garden approach. Data lived in siloed mainframes, guarded by permissioned access and centralized trust authorities. But on a decentralized ledger, this walled garden is stripped away. Every interaction is recorded, and even if the transaction payload is hashed and unreadable, the act of transacting leaves a structural footprint. This creates a critical vulnerability known as metadata leakage. An observer may not see the raw data, but the who, the when, and the how of a transaction remain entirely visible on the chain. Security researchers classify these metadata leaks into a 7-tier framework, L1 through L7 linkability. This framework maps the exact methods attackers use to de-anonymize users through statistical correlation. This network graph illustrates L1 and L2 linkability. By tracing the timing and frequency of transactions between anonymous wallet addresses, an observer can map the exact organizational partnerships and business relations taking place off-chain. L6 linkability exploits time. By analyzing the exact timestamps of a user's on-chain activity, attackers can pinpoint the geographic origin and specific time zone of an organization. These vulnerabilities break down entirely in a collaborative feedback system. In a joint enterprise project, reputation data and performance ratings must be aggregated without ever being linked to specific project members. Standard role-based access control, a system that restricts network access based on a user's assigned title, fails to solve this. The roles themselves become a linkability vector, allowing an observer to deduce a user's identity simply by watching the permissions they exercise. Privacy in a decentralized system is not a binary state of encrypted versus unencrypted. It is a structural engineering problem that requires the complete decoupling of metadata from the action itself. The mathematical solutions to these linkability vectors have been heavily researched at academic hubs like the University of Waterloo, leading to specific proof-of-concept models for privacy-aware collaborations. The primary goal of this research is highly specific. Design a decentralized system that can compute an average project feedback score without exposing the identity of the voters, the time they voted, or the individual values of their scores. This architectural flowchart outlines the resulting trifold structure. The transaction must pass through 3 distinct cryptographic gates: a Merkle tree, a range proof, and poly-A cryptography. This modular architecture treats privacy as a sequential engineering pipeline, rather than relying on a single, heavy encryption layer to hide the entire transaction. Together, these gates form a zero-knowledge engine. It can ingest data, run complex verification logic, and output a mathematically proven result, while keeping its internal state completely opaque to the public ledger. The engine's first requirement is anonymous authentication. A user must prove they are an authorized member of a specific project group without revealing exactly which member they are. This is solved using a Merkle tree operating inside a zero-knowledge proof. Instead of storing a list of authorized wallet addresses, the smart contract only stores a single cryptographic root hash representing the entire group. This Merkle tree diagram illustrates the off-chain proof generation. The user hashes their specific wallet address, acting as the leaf node, and provides the exact mathematical path required to reach the known root hash. This calculation is processed through a Circum circuit. Circum is a programming language designed specifically to write zero-knowledge logic. The circuit verifies that the user's secret leaf and path perfectly reconstruct the root, without ever disclosing the leaf itself. The circuit generates a succinct, mathematically binding proof, which the user then submits to the on-chain verifying contract. This severs the L2 linkability vector. The blockchain network mathematically verifies that a valid group member interacted with the contract, but it has no way to determine which specific member it was, breaking the connection between the address and the action. The integrity of this gate relies on a cryptographic property called knowledge soundness. A dishonest actor cannot simply guess or forge a valid path to the Merkle root.
By successfully clearing Gate 1, the system securely anonymizes the who of the collaborative transaction. The second requirement addresses time. The system must enforce a strict project deadline for submitting feedback, but it cannot record the actual submission timestamp on the ledger. This timeline shows the mechanics of a zero-knowledge range proof. The user must prove that their hidden submission time exists entirely within a public boundary, specifically between the project close date and the final delay deadline. To generate this proof, the user's hidden timestamp is evaluated off-chain using circumcomparator logic, checking that the value is strictly greater than the start time and less than the deadline. The smart contract then accepts this generated proof. It only receives the mathematical assertion that the temporal constraints were satisfied. It never sees the underlying time variable. This eliminates L6 linkability. Because the exact timestamp is never logged, an outside attacker has no data points to correlate submission times with geographic time zones or office hours. Standard blockchain architectures rely on block timestamps for sequencing, but using block time for user validation leaves a permanent, highly specific footprint. Gate 2 completely decouples the when from the ledger's permanent record. The final requirement is processing the data itself. The system needs to calculate an average project rating without exposing the individual feedback scores submitted by each organization. This mathematical visualization demonstrates Palier homomorphic encryption. Palier is a cryptographic system that allows mathematical operations to be performed directly on encrypted data. Here, the multiplication of two encrypted ciphertexts is mathematically equivalent to the encryption of their sum. The smart contract acts as a blind aggregator. As authorized users submit their encrypted ratings, the contract multiplies the ciphertext together, maintaining a running, encrypted sum of all feedback. Once the voting period closes, the final encrypted sum is taken off-chain. Only the specific project owner holding the correct private key can decrypt the aggregated total to calculate the average. This neutralizes L5 linkability. No participant, validator, or outside observer can see the individual ratings, making it impossible to deduce patterns of organizational satisfaction or internal politics. Gate 3 secures the what, ensuring that sensitive business intelligence is completely obscured during the aggregation process. When executed in a simulated environment, this zero-knowledge feedback system performs exactly as designed. This table visualizes the results. For authorized on-time participants, the system returns true for Merkle and range proofs. Their ratings aggregate to an average score of 87. If a participant submits late, the range proof flags false, blocking their rating from the final summation. Similarly, if a fake member attempts to submit a score, they fail the initial Merkle membership proof, and their input is immediately discarded. The proof of concept confirms that the system operates as an incorruptible, completely blind referee for collaborative data. However, this absolute privacy comes with a strict engineering trade-off. Executing zero-knowledge proof verification directly on a Layer 1 blockchain requires massive gas costs. This bar chart maps the execution costs. Verifying the ZK Snark Merkle and range proofs consumes nearly 300,000 units of gas each, making them vastly more expensive than the Palier homomorphic sum. To understand these limitations, engineers focus on succinctness and trusted setups. Succinctness keeps a proof size small enough to verify quickly. A trusted setup is the sensitive initial cryptographic ceremony required to generate the system's parameters. Optimizing both is notoriously difficult. To solve these gas costs, leaders in the space, like Ethereum co-founder Vitalik Buterin, are pushing development toward Layer 2 solutions. By moving the heavy proof verification to off-chain networks, often called ZK rollups, the costs are drastically reduced before the final state is settled on the mainnet. While Layer 1 verification remains cost-prohibitive today, the modular logic of this zero-knowledge engine provides the exact blueprint required for private enterprise collaboration. Metadata linkability is now a solved mathematical problem. The challenge for the next decade of blockchain architecture is simply making that mathematics economically efficient.